Okay, my name is Anar, and I will describe our paper titled Fast Spatial Autocorrelation. And here is our team, mainly from Stony Brook University. So first, I'll give a brief description of the spatial autocorrelation as a statistic. It's some of the existing approaches and their problems. And then after that, I will describe the SA, or our statistic, the intuition behind it, its formal definition, and the algorithm for computation. And then after that, I'll give some brief examples. And then I will follow with some theoretical properties of SA, some of the convergence guarantees, and invariance under linear transforms. So then finally, I will finish with some results from the experimental evaluation with some running time considerations and some sensitivity analysis. So what is spatial autocorrelation? Spatial autocorrelation is, well, first of all, what is correlation, right? Correlation computes the level of association of two variables, in this case, X and Y, and it gives a scalar number. Autocorrelation instead computes the association of variable Z with itself, but with some lag. So in case of a lag L, it's essentially a correlation with ZI of ZI plus L. Now, how about spatial autocorrelation? Spatial autocorrelation is something that's bidirectional. It's a little bit more involved. And then in any data where there is spatial coordinates present, the exact coordinates matter. So we have to take into account the exact locations of coordinates. And there has been some very early work done on the spatial autocorrelation, namely starting with Moran's statistics in 1950 and Geary's statistics a little bit later. And they both essentially compute the statistic based on a double summation over all data points indexed by I and J, and incorporating the weight between data point I and J. That's in some way dependent on the distance. And then there's the two different types of kernels involved, and that distinguishes the two statistics. But then the problem with them is that they're both quadratic in time. So you have to make at least n squared computations to be able to compute the Moran's I and Geary's C. And that quickly becomes a problem even with the moderate size data. Now, how do we sort of approach the problem? How do we try to make it faster? Essentially, the intuition is that as we join clusters, as we take a bunch of points that are spatially distributed and join them into clusters, the variance inside the clusters should increase in a manner that depends on what the spatial autocorrelation of the variable is. So formally, we would take the variable Z, Zi, some feature, and then for each Zi, there would be a spatial coordinate attached to it, Xi, and this X can be in 2 dimensions, 3 dimensions, more, that's somewhat general. And then there would be an agglomeration order we would need defined on the coordinates. So the merge order has to be solely function of the coordinates Xi. And then we would want to get an output that is a scalar quantity between -1 and 1. And well, how do we do that? We essentially keep track of the intra-cluster sum of squared deviations. So the intuition is that basically once the agglomeration order is started, all the points are singletons. They're the clusters themselves. So within those clusters, each cluster is a singleton and their variance is 0. So things start out on the left at 0. Now, as the clusters are joined into larger and larger clusters, this variance is bound to increase. But then how exactly it increases is a concern to us. And eventually it's supposed to hit n-1 times the variance of the variable. And in units of this n-1 variance squared, n-1 variance, we eventually should get to 1. But exactly the shape that it takes to get to 1 from 0 is what's interesting to us. So in an elevation example, it looks like the variance is increasing very slowly. And that tells us that this sort of, the variable of elevation might be something very spatially correlated. Now, how do we compute it? We compute it by keeping track of the clusters, their mean values of the variable z, and their cluster centroids. And finally, we need to keep track of the sum of the square deviations, which is the main workhorse of our statistic. So the cluster 1 and cluster 2, C1 and C2, are joined into C12, cluster 1, 2. And then the mean value of the feature Z bar of C1 and Z bar of C2, they're averaged into Z bar of C12. And then the same thing happens with cluster centroids. And the sum of square deviations is kept track of by sort of from the previous time step, from the previous merge, we incrementally add the 2 terms over here on the right. And that sort of accomplishes the keeping track of the sum of squares. Now, once we kept track of the sum of squares, we can average them and we can normalize them by its final value, the sum of squared at n-1 steps. And then we do a small linear transformation to get it to be of the right sign, of the right range between -1 and 1, and increasing when spatial autocorrelation is more. And that is essentially our statistic assay. And each merge operation, each update on the left here takes a constant amount of time. And with n-1 merges, to go from singletons to a single big cluster of all points, we would get a linear time complexity of the statistic computation. So now some examples. What does it look like? So in our elevation case, if we linearly transform to get the right sign, the sort of trace of the sum of squares, we get something like this on the bottom left. And the accompanying variable elevation looks like it's something that's very slowly varying. The elevation doesn't change much until you get from the eastern United States to the western United States, to the Rocky Mountains. And this is, by the way, on the data of the sort of demographic and geographic variables from US counties, which includes some a little bit above 3,000 maybe examples. So then another example would be the population density in the US, which shows a very low spatial autocorrelation, or something that says the population density is negatively autocorrelated, that the sort of the variance shoots up very quickly as we start joining clusters. And then, we can see from the map that the cities, the big cities, can be right next to very low density suburban or rural areas. And that happens frequently, especially on the East Coast in the United States. So that tells us that we're capturing the sort of lack of autocorrelation of the population density. So now, how does it compare? How does SA compare to the previous measures, as the Geary C and Moran I? So we more or less see that the Geary C is strongly anti-correlated with SA, and Moran's I is strongly correlated. So at this point, we can say that if we plot the scatter of the SA against the two of the measures for the county variables, we get that they're clearly so there's clearly strong correlation, and we're picking up what both the Geary C and Moran's I are picking up. Now, here's a theoretical property of the statistic that given a random variable as the feature that we're computing autocorrelation of, and in the limit of large number of samples, we are bound to get 0. And that sort of gets proven by the fact that we essentially look at the trace of the sum of squares, and we try to show that it follows more or less sort of at a uniform pace. It increases from 0 to its eventual value. And to do that, we reason by way of showing that expectation of these jumps the heights of these slabs at each merge event is actually sigma squared, the variance of the variable. And in the limit of large number of data points, the contribution or the deviation from this expectation becomes small, and essentially this line is more or less a straight line with a constant slope. So that sort of more or less proves that the expectation goes to 0. And now runtime considerations. So here we show the two different stages of the computation where we split it into the merge order computation on the coordinates of the data points and the computation of the statistic on the sort of the feature variables, the z's, given the merge order. And here our metric compares very favorably to Moran-Zai and Geary-C, that all the computations of the statistic given the merge order can be done within 1 second up until some 63,000 data points for our metric. And then for Geary and Moran, it can take from 2 to 3 and almost 4 hours to compute. So that's sort of the difference between the quadratic complexity of the Geary-C and then the linear complexity of our metric. Now here is some display of what we think is the improved sensitivity to the true autocorrelation in the data. So to measure the true autocorrelation, to recover it, we have to actually build it into the data synthetically. So we took IID distributed random values and in uniformly sampled coordinates. And then we did an experiment with sort of building into the data a sort of a known autocorrelation by doing a disk averaging experiment. And the larger the disk average, or the disk over which the averaging is done, the more autocorrelated the variable becomes. So then once we measure what Geary-C, Moran-Zai, and SA can compute on this sort of data with known autocorrelation, we can see that SA starts seeing the increasing spatial autocorrelation much earlier. So in the first, on the left black dashed vertical line, we can see that the half of the range of the SA from 0 to 1 is actually reached some half an order of magnitude earlier than in case of the Geary-C and Moran-Zai. So the Geary-C and Moran-Zai start seeing the same sort of level of increase of autocorrelation about half an order of magnitude later in the second vertical line. And then sort of there's some sort of observation that both Geary-C and Moran-Zai are much more noisy on the right side of the graph when the autocorrelation is much larger, and it even actually reverses directions, which is sort of can be very misleading. Whereas SA is sort of, the error bounds are much narrower on SA, and then sort of the direction reversing is not as prominent. Now, because we are doing the computation in 2 stages, the merge order calculation and then the statistic calculation, we can have additional savings if the merge order that we computed once can be recycled. So in a very useful example for such a problem, we can consider the fMRI or the functional MRI data, where we essentially have some sort of voxels or 3D pixels in the brain that gives out data, but then the coordinates of these sort of voxels never change throughout the sort of the experiment. And then each of the locations give out time series. So there are many features. And in our case, M, which is the number of time steps that is present in the time series, is something, it can be something along the lines of several thousand. So in our case, it's 4,640. And the number of data points, the number of voxels in the brain can be something along the lines of 130,000. Now, at this stage, by recycling the merge order computed already once, we can we can do this merge order computation in case of a single linkage clustering, spending the n log n time once, and then after that, we would do the sort of linear complexity statistic calculation m number of times, giving n log n plus mn complexity. And that compares very favorably to Geary C and Moran's I, where you have to do the n squared calculation m number of times to be able to compute their statistic, the sort of the C and I for m number of time steps that's present in the data. So then essentially we were able to see that each time step of the SA calculation on each each time step of the sort of time series can be done in under 1 second, which actually turned out to be faster than the sampling rate of our fMRI data, which gives a sort of a whole brain picture at 0.8 seconds. Now, unfortunately, with Geary C and Moran's I, due to the memory requirements of sort of n squared memory requirements, given n is about 130,000, we were not able to compute the comparable statistics. So we don't have time for Geary C and Moran I for this case. So with that, I have to summarize the work that we've done and claim that we were able to compute linear sort of the spatial autocorrelation in linear time in case merge order is known already. And then we were also able to sort of give some examples that, you know, single linkage can be computed in n log n time, and average linkage and other sort of cases can be computed in a slower time. And then we showed that the SA that we computed, the spatial autocorrelation, correlates very well with what traditional measures obtain. And also we obtain further savings if we recycle the merge order that we computed once and use it again. And we get a sort of complexity of the order of n log n plus mn instead of the m times n squared, which traditional methods would have given. And that is it. Thank you very much.